Well, welcome back, everyone. This is beginning the last third of the class, so thanks for hanging in there with us. Um, what I'd like to do is start a series of lectures talking about two topics. The topic of matching, which is related to the topic we had last week when we talked about confounding. And then I'm going to talk about a topic called effect modification, which really has nothing to do with confounding, but unfortunately is often confused with the topic of confounding. So we'll talk about that in a few lectures. But let's now begin talking about this concept of matching in epidemiology studies. Now remember the last time we were together at least, we talked about what we could do in the design of a study to minimize the potential that a factor might be a confounder in the resulting data that we collect from the study. We talked about randomization in experimental studies and how it balances the two groups you're comparing, how the coin flip will put just as many old people in one treatment group as in another, so that the age distribution in the two groups you are comparing are similar. The groups are exchangeable in terms of a concept we talked about last time. We talked about another type of design feature to avoid the potential of confounding. It's restriction. And there are a couple of levels of restriction. Restriction limits the potential for some people being in your study. So it's a feature of the design of a study by which only certain people have a possibility of entering in a study. So in the extreme case, you might restrict your study to only enroll men. Let's suppose we want to know whether smoking increases a person's risk of heart disease. We're going to do a cohort study. We're going to take a bunch of smokers and non-smokers, follow them for a period of time, measure their incidence of heart disease, calculate a risk ratio, and report that as our estimate of the effect of smoking on heart disease. Well, what if I only enrolled men in that study? I had a bunch of smokers who were men, a bunch of non-smokers who were men. Any measure of association I observe in that data set cannot be confounded by sex, because whatever influence male sex has on your risk of developing heart disease, it's going to have the same influence in the smoking group and in the non-smoking group because everybody in the study is male. It's a very good study for answering the question, what's the effect of smoking among men? But it's a lousy study for asking the question, what's the effect of smoking among women? So the problem with restriction of that extreme amount is generalizability. You can't infer from your data what the effect of smoking would be for the type of person who doesn't get into your study, women in that case. Well, there's another type of restriction I want to talk about today. I mentioned it last time. It's matching. Matching, again, restricts some people's chances of getting in the study, but it restricts only some people, not all people. So unlike restricting your study to be men, which leaves out all women, if you match on a factor like age, maybe it won't be possible that a 69-year-old person could get into your study. Maybe a 68-year-old person could, maybe a 70-year-old person could, but it might be that anyone who's 69 has no chance of being in your study. Well, you might stop and say, well, how can that be? What's so wrong about being 69 and what's so right about being 68 or 70 that the 68-year-old and the 70-year-old can get into my study, but the 69-year-old cannot? Well, that happens when we do observational studies, cohort studies, case control studies, and we match. So again, let's think about smoking as our exposure, coronary heart disease as our outcome. We're going to match on age, first in a cohort study. And the way that's going to work is that matching implication that we're matching on age is probably going to restrict who's going to get into your group into your study, I should say, in the comparison group. It's going to restrict a non-smoker's chances of getting into my study. And the way it does that is the following. I start my study by enrolling my smokers, and as I enroll each of them, I ask, how old are you? If a person says they're 68, a 68-year-old smoker, I go out and find a 68-year-old non-smoker. If the smoker says they're 70, I go out and find a 70-year-old non-smoker. But if I have no smokers who say they're 69, I never go look for a 69-year-old non-smoker. So it is restricting the chances of some people being selected into my cohort study in the non-smoking group, because you have to get into my study, you have to have the same age as one of my smokers. Same thing can happen in case control studies. Again, let's think about smoking as heart disease as our example with age as our matching factor. Case control study, I start out with people who already have heart disease, my cases. I enroll other people as my controls, usually people who don't have heart disease. As I enroll my cases, I ask, how old are you? If the case says they're 68, I find a 68-year-old control. If the case says they're 70, I go out and find a 70-year-old control. If I have no 69-year-old cases, I end up with no 69-year-old controls. So it's again restricting a potential control's chances for getting into my study. Well, why do we do this? What's the motivation for matching? And I think if you ask people, why did you match in this study? 99.9% of them are going to say, I did it because I wanted to avoid confounding. I want to make my two comparison groups, my smokers and my non-smokers in my cohort study, or my cases and my controls in my case control study, I wanted them to look comparable with respect to having the same age distribution because that's the reason I matched on it. So let's talk about the implications. Does matching avoid confounding? Well, the answer is yes and no. There's some good news. And the good news is if you do a cohort study and you match one-to-one, say, every 68-year-old smoker, you find a 68-year-old non-smoker. Every 70-year-old smoker, you find a 70-year-old non-smoker. What you're going to end up with when you finish your enrollment is exactly the same age distribution among your smokers as you will see among your non-smokers. That's what matching does for you. So what matching does in a cohort study, it addresses the relationship between the potential confounder, say age in that particular example I've been looking at, and the exposure, which was smoking. If I match one-to-one, non-smokers to smokers, by a common age, then at the end of the enrollment process, there'll be no relationship left over in the data set between the confounder age, the potential confounder, I should say, age, and the exposure smoking. That relationship that a confounder has to have, the confounder member has to be related to the exposure, will not happen in that data set. Therefore, matching with a fixed matching ratio like one non-smoker to every smoker will avoid confounding in cohort studies. That's the good news. Well, here's the somewhat, not terrible news, not bad news, but somewhat less good news. What about case control studies? Let's suppose I enroll a person who has heart disease as a case, ask his age at 68, I find a 68-year-old control, and I do that for all my cases, find one control for each case with the same age. Does that avoid confounding? And the answer is not quite. You still have to do an adjustment for the matching factor in the analysis, and I'll give you an example in the next lecture why that's so. But conceptually, the reason is the following. Remember, this is what a confounder has to have. It has to provide a backdoor pathway to give an alternative explanation why the exposed people could get more disease than the non-exposed people. It has to be related to the exposure. And I said in a cohort study, matching blocks that relationship. And it also has to be an independent risk factor for the outcome. It's this other arrow connecting the potential confounder to the outcome that we are trying to block when we match in case control studies. That's the target. The reason we're matching is we want to block that independent relationship between the confounder and the outcome so that when we enroll people in our study, we will not have confounding by the factor we matched on, say by age. The problem is there are two reasons as I look at my cases and select their match controls, matching by age. There are two reasons I might see a lot of old people among my cases. The two reasons are that if age is my potential confounder and CHD, coronary heart disease, is my outcome, there are two potential mechanisms by which old people could end up being cases in your study. Old age itself influences the risk of having disease, so older people are going to be more likely to be cases. But remember, old age might also be related to whether you smoke or you don't smoke. And smoking brings with it higher risk of getting heart disease. So there's another reason why you might find old people among your cases. So age has, again, now two pathways linking it to the outcome, coronary heart disease. Its direct mechanism that you're trying to block with matching, and this backdoor pathway it has through smoking in this case. So that's the problem. When you match it, you're really impacting both of these relationships. The independent one you're trying to measure that smoking has on the outcome, and the one you're trying to block by matching, the independent pathway between, in this case, age and your outcome. So the impact is it impacts on both of these arrows, and that's the problem with matching in case control studies. And I'll show you an example to try to tease that home in a minute in our next lecture. But this is a summary or the problem we have with case control studies. When we match on a potential confounder in a case control study, what do? We build similar distributions of that confounder with the cases and the controls. So if my outcome is coronary heart disease, my cases are people with heart disease, my controls, let's suppose they're people without heart disease, if every control is matched one by one to a case by age, then when the study enrollment ends, the age distribution of the cases will be exactly the same, not just similar, exactly the same as my controls. My controls look just like the cases with respect to age. Well, if they look just like the cases with respect to age, they're going to look just like the cases with respect to any other factor that's correlated with age. So let's suppose smoking is highly correlated with age. Older people say smoke and younger people don't. When I look at my cases and controls and see they have the same age distribution, they may well have the same distribution of smoking because older age brings with it into the controls more smokers. And as a result, when I build my analysis to look at the smoking histories of my cases compared to the smoking history of my controls and look at the odds ratios like we did for case control studies, we're going to get a result that's going to be biased towards the null value. It's going to underestimate the true effect of the exposure. Well, that's what I'd like to show you next in the next lecture using an example. So I'm going to stop now and see you next time.